Alright, this video is going to walk you through the car buzzer project, how to progress through each of these 6 steps, obviously not being able to do building the physical circuit, but getting you up to that point. So in this car buzzer project, we have the following statement. We are going to make a circuit that makes a buzzer sound depending on a few inputs. The scenario is the buzzer should sound only when the key is in the ignition and the driver's side door is open or the seatbelt is unbuckled. Using this statement, you will progress through the following 6 steps to design your circuit. First, generate 1-0 logic for each input of the circuit. What that means is come up with the true statements. When is an action happening when it's equal to 1, and when is an action happening when it's equal to 0. Then you create your 3 input and 1 output truth table and generate the min terms for the table. Now, we haven't gone over min terms in depth, but I'll describe those in just a moment. We then write a Boolean expression for the min terms, draw the circuit in your EMBs, you should all be doing this, and lastly, construct the circuit in MultiSIM and test it to verify that they match the truth table. So let's get started with this. Here in MultiSIM, I've just copied over some information. This first text box states that the buzzer should sound only when the key is in the ignition and one of these two scenarios are also being met. The door is open or the seatbelt is unbuckled. From there, I assigned a true and a false value to each of these statements. Now for this activity, you should use the same statements I use. However, if you have different statements in future projects because it makes more logical sense, then use what most makes sense to you. For example, saying the seatbelt is buckled equals 1 isn't quite logical here because then it forces me to use an inverter gate, and we'll go over that in just a moment. But after I've dissected this statement, I come up with my true statements. When the buzzer is on, I'm giving an output of 1, a high value. When the key is in the ignition, I'm giving an output of 1. When the door is open, I'm giving an output of 1. And when the seatbelt is buckled, I'm giving an output of 1. Now I'm saying output, but remember, the key, the door, and the seatbelt are all inputs. And the one output is the buzzer. Based on that, I've come up with the following truth table, which you can see here. I have 3 inputs, K, D, and S for key, door, seatbelt, and 1 output, B, for buzzer. Now I have to work through this truth table to generate all of these outcomes. I don't know what these are, but I can work through line by line with this truth table and determine what the output is. For instance, on line number 1, I read this as the key is not in the ignition, because when the key is in the ignition, we should see a 1. The door is closed, and the seatbelt is unbuckled. Remember, seatbelt buckled equals 1. So, is my buzzer going off here? No. So it's a 0. In the next statement, the key is not in the ignition still, the door is not open, and my seatbelt is buckled. So I definitely shouldn't have my buzzer going off here. My output is 0. Now using logic here, looking back at our original scenario, the key is in the ignition and, meaning the key must be in the ignition and something else has to happen for this to occur. Because the key is not in the ignition on this row, it's a 0. And on this row, it's also an output of 0. It has to be, because the key is not in the ignition. Now this next line, I read this as the key is in the ignition, the door is closed, and the seatbelt is unbuckled. Remember, seatbelt buckled equals 1, seatbelt unbuckled equals 0. My statement said that the buzzer should sound when the key is in the ignition, true, and when the seatbelt is unbuckled, true. So this output is a 1. Now here, key's still in the ignition, door's still closed, but I've buckled my seatbelt, so the output is 0. For this line, the second to last one, the key is in the ignition and the door is open, So my buzzer should be sounding. And the very last statement here, the key is in the ignition, the door is open, and the seatbelt is buckled. Now the seatbelt's buckled, so you might think, oh, my buzzer shouldn't be going off. But remember, it's the door is open or the seatbelt is unbuckled. The door is open. Oops, let me undo that. The door is open per this one right here. So my output is a 1. That is my completed truth table. Yours should match what mine looks like. If it does not, make your changes. From that, I can create the following Boolean expression. B for buzzer is true is a 1 when K for the key and D or not S are all 1. Remember, we only care about what's happening when things are true. I don't care what happens when my seatbelt's buckled, my door is closed, and the key's not in the ignition. I only care when those values are 1. So I read this as K and D or not S. Now this tilde sign means not S because it's in type. In writing, you may see that bar over the top of it. Either one is appropriate here. So this is my Boolean expression. Now looking at this Boolean expression, I can tell 3 things about my logic gates that I need. The first is that I need 1 inverter for not S. The second is that I need an OR gate with this plus sign right here. And I need an AND gate. These parentheses mean multiplication, but in digital electronics it means AND. Because remember, this is K and D or not S. So that gives us the following circuit above. I have 3 inputs, 3 switches, K at the top, D, and S. And they're wired to VCC for my high signal and ground for my low signal. Now you'll notice that key is at the top and it's connected to the leftmost probe. Because if we look at our truth table, K is our most significant bit. So it should be the topmost switch and the leftmost LED probe. That is important when we count in binary, which I will demonstrate once the circuit is complete. So let's build this circuit. I'm going to bring this Boolean expression up with me as well. All right, I've got my Boolean expression and I've got my truth table. I'm going to place some components here to get started building the circuit. The first thing is this not S. Now I know that that is a 74LS04, and as I search, nothing's coming up because I'm just looking in indicators. So remember, when you search, search everywhere. All families, all groups. 74LS04 brings up multiple different options. Now in this video, I am going to use the logic gate. In the video that will follow this one, I am going to use the IC chip. I'm going to use both because one I use in MultiSIM, the other I use physically breadboarding. I also know this is a hex inverter, and you'll notice I said not S earlier for the seatbelt. So if I type in the word not, bam, there it is. It's an inverter. So I'm going to drag and connect that there. I also know I need an OR gate, so I'm going to search for OR. Now, none of these look like the right one until I get to this one. There are multiple different types of OR gates, AND gates, inverters, all sorts of logic gates. Make sure you choose the correct one. And then I need a 2-input AND gate as well. Again, making sure I select the right thing. Now let's look at my Boolean expression. When breaking down the expression, you work from the inside out, just like you would in a math problem. If I had a math problem that said 3 parentheses 3 minus 4, I would do the 3 minus 4 portion first because it's inside the parentheses. The same is the case for Boolean expressions. Inside the parentheses, I have D or not S. Currently, these 3 lines, these 3 wires, are K, D, and S. And I'm going to make a note of that by using Control-Alt-W, or maybe it's Control-Shift-W, or I'm sorry, Control-A. Control-Alt-A to write a text box. And I'm going to write S, Control Alt A, D, Control Alt A, and K. Now I know that these three lines, these three wires, are the following inputs. And I'm going to just make them look a little better. K, D, and S. Well, to get not S, I have to run it through an inverter. So all I have to do, connect it to an inverter, and then I get my output. And then I'm saying D or not S. So drag this over to make more space. Here comes D. Here is OR. So now using that text feature again, I'm going to say that this became not S. And now on the output, this is D or not S. If it helps you to label each and every single one of your wires, do so. It's only going to be to your benefit, and it helps you stay organized. But now I can read through this, and I see that here I started with S. I inverted it, so it became not S. And then I put it into an OR gate with D. I'm even going to copy this and put it down here. So now I know that this is D or not S. If you want to go crazy with the labeling like I've done and put them on every output and every input, do so. It only helps you. So I've done my parentheses. This is D or not S. Now I have to bring in this K. And I know that parentheses means and, so I'm going to say and K. So here's my AND gate. Here's my D or not S. And in fact, let me do this with it. Now I can drag this AND gate all the way down here, drag in my K input, wire in my D or not S input, apply my labels, and now on this output I have K and D or not S. And I'm going to wire this into a probe. Let's go with orange. Again, whatever colors you choose, however you choose to organize this, completely up to you. So I've got my circuit and I've got my Boolean table here. Now I'm going to make this a little bigger so that we can read it together. And you'll see it messes with the formatting, so apologies for that. But now let's talk about what I mentioned earlier, counting in binary. If I look at this truth table, I can see that when K is 0, D is 0, and S is 0, my output should be 0. So I'm going to simulate this. Right now, K is 0, D is 0, S is 0, so my output buzzer is 0. Notice when I go to 0, 0, 1, I have to light up this probe. That probe is my S probe, my seatbelt. So 0, 0, 1, my output is 0. Let's go to 0, 1, 0. 0, 1, 0, output's still 0. So far, so good. Let's go to 0, 1, 1, 0, 1, 1, output's still off. Now, we're about to transition into 1, 0, 0. So my output should be on. Let's see what happens. 1, 0, 0, and my output is in fact on. Because remember, this is saying that the key is in the ignition and the seatbelt is not buckled. And currently, it is not. Now, if I buckle the seatbelt, if I go to 1, 0, 1, notice what happened to my output. It turned off. Let's go to 1, 1, 0. My key is in the ignition, my door is wide open, and my seatbelt's unbuckled. That buzzer's going off. Now let's buckle my seatbelt, but I'm going to keep the door open. 1, 1, 1. Key is in the ignition, door is open, seatbelt is buckled, but because my door is open and the key is in the ignition, the red and green probes, my buzzer is on. And if you're wondering how I was toggling through these switches, I assign Q, W, and E to these switches. Use whatever assignments make sense to you. Click on them manually if you prefer that. For me, being able to go 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on and so forth is so easy because these switches are in line. They are they are going from left to right, Q, W, E, or even 1, 2, 3, or A, S, D, so on and so forth. Use whatever makes the most sense to you. So that's the end of this video. This is the circuit you should have. This is the truth table you should have, as well as the following outcomes. It should match accordingly when you simulate this. In the next video that I'm going to provide, I will use the same circuit. However, I'm going to wire in IC chips, like I was actually going to breadboard this. And we'll talk about how I'll do that in that video.